All of you got the quiz 2 results, right?
Yes, madam, we got.
Okay. Okay. So how was it?
I've not scored well actually because I couldn't prepare. I was not here in India itself for last 20 days.
Okay. What about others? Okay. Okay. So let's start. So this is the starting lecture of graph theory, and in term also the majority part will be from the graph theory. Okay. So try to learn the graph theory portion properly.
Is there any prerequisite for graph theory?
No. We are starting from very basic. Only the some method, some life problems, and some definition. That's okay. Okay. So graph theory is the main two element of graph theory is basically we can call as point and line, right? So with if you want to draw some graph, so what do you need? The basic thing is point and line, right? Nothing more we need. So the points and lines. So lines means we will have two endpoints. So here in graph theory, we will call the points as vertex, okay, and the lines as edges, okay. Uh, so basically, what is the edge? If you have two vertex and just connect them, then you will get the edge, okay, which is the edge connected connecting to vertex 1 and vertex 2. So these vertex and edge, these are the main element of our graph theory, okay. So we will like define some definition, some concept based on these two things. Now we have two type of graph. Is one is directed graph, and the second one is undirected graph, right? What is directed graph? Anyone?
So you have a narrow pointing from one vertex to the other.
Yeah. So in directed graph, we will use a arrow. That means we will mention the direction. So if we have one vertex, we have another vertex. Again, we can repeat the same. So the directed graph, this means basically we have the edge from 1 to 2, and this means we have the edge from 2 to 1. So here we are mentioning the direction. That is why we call this edges as directed edge. And if I draw a proper graph using directed edges, then we will call the graph as directed graph, right? So this is what? This is a edge from 2 to 1, right? And what is undirected graph?
You just join them by a simple straight line, right?
Correct. So if I have two different vertex and if I just join them with a straight line, this is undirected graph, okay. So this is actually what this is means. We have a edge from 1 to 2 and we have another edge from 2 to 1, right? That means both side we have. So then it is basically like that. So we basically avoid writing this two-sided arrow and we use the notation as a simple straight line. When this is basically undirected edge. Now when we use undirected edge throughout our graph, then the graph is basically undirected graph, right?
But it's indirectly directed, right, ma'am? Because since we are saying there are no arrows, it's assumed that it's a both direction.
Yeah, that means no, it is not indirectly directed because it has the both side. So for all the edges, we have both side, right? So we don't need to be worried about the direction na, here.
Okay.
Right? So the thing is, suppose you have one graph, 1 to 2 and 2 to 3, okay, like that. Now, can I go 1 to 3 with this graph, in this graph?
No, you cannot.
We cannot, right?
Yeah.
But if I have this, then we can go, right?
Correct.
So this is the difference. These two are not same, okay? So here we have to follow the direction. We can't go beyond the direction. But for undirected graph, we have the independence, right? We can go from any vertex to another any vertex, right?
Okay.
Yeah. So basically we have two type of graph, directed graph and undirected graph. Then we have path. So from the word path, it is very clear, right? So that means it's a track from one vertex to another vertex. Now we can't like sometime if I have this type of graph, suppose yeah. So suppose if I have this graph, then I want to find the path from 1 to 3. So you can see there is no direct path from 1 to 3, but I can go 1 to 2, then 2 to 3, right? So in this way, we can define a path. So if I define the path, so what is the definition of path? We can say it's basically sequence of, we can denote it as sequence of vertices some V1, V2, Vk connected by edges, right? So this is the definition of path. Okay. Now, if I suppose want to, for example, I want to find the path between 1 to 3. Okay. So what are the possible paths from 1 to 3?
You can go via 2 and you can go via 1 to 4 to 3.
Correct. So we have an 1, 2, then 3. Another we have 1, then 2, then 4, then 3, right? These two we have. So these two are possible path from 1 to 3, right? So what is a remark is in path, when we are defining path, basically we can't repeat vertex in path, okay? We know that in sequence, we can't repeat a place, right? So in one place, we have to put one number, right? So like that also, we can't repeat a vertex in path. But there can be some way so that a vertex is getting repeated. So in this type of way, what can we say that? A walk, right? So what is a walk? Is basically a path where vertex can repeat, right? And in path, in path, we can't repeat vertex. Okay. Clear? Any doubt? Any doubt up to now?
No, ma'am. Go ahead.
Okay. Okay. So next we have a problem. So the problem is named is graph coloring. Okay. So what is the main motto here? If we have a graph, we have to pick the minimum possible number of color need to color the graph. That means basically we have a graph, suppose, and we have to color the vertices of the graph such that no two vertex which are like connected by a direct edge will not have a same color, right? So the problem is like how many color we need to do that, right? So what is the procedure? So here we can express the coloring thing mathematically. So if I take the graph, G is our graph, and we can express it as V comma E, where this G is graph and V symbolizes the set of all vertices and E symbolizes the set of all edges. Okay. Okay. Now the coloring, we can look the coloring as a function C from V to, this is a small c, this is a capital C. Okay. So C is like the set of all vertex after putting the color. Okay. So the colored vertex. Okay. So such that we have a condition u comma v. Suppose this is the age. What is u comma v? That means this is the age from u to v. Okay, it can be directed, it can be undirected. This is the age from u to v. Okay. So if I have a age from u to v, we can denote it as u comma v. And we know that capital E is our set of all ages. So it will imply that C of u is not equals to C of v. That means whenever we have two vertices which are connected by a edge, directly connected by a edge, that means they will not have the same color. Okay. So in this way, we can express the coloring problem with the function. Is there any doubt here?
Ma'am, can you please repeat? I couldn't understand this concept.
Okay. So did you get what a coloring problem is?
No, it was overboard.
Okay, okay. So coloring problem is like, suppose if you have a graph, okay. For example, we suppose have this graph,
Okay.
and we have to color the vertices. That means V is the set of all vertices, right? So
Yeah.
what is V? So we have
Here 1, 2, 3, 4.
Correct. And E is set of all edges, right?
Yeah.
Then what do we have? 1, 2, 2,
2,
1.
3, 2, 3. Okay, 2, 1, 2, 3, 3, 2. The 3, 4, 4, 3.
Correct. This is the edges, right?
Right.
Now our problem is we have to color the vertices like 1, 2, 3, 4. You have to put a color in the vertices, but the condition is we can't put same color to those vertices which are connected by a single edge, like which are directly connected.
So that means, for example, if I put a blue on the number 1,
Then
I
we
cannot
can't
put
put
a
the
blue
same
on
blue
the
2.
2. It
Yes.
can be 3 or 4, but it cannot be 2.
Yes, correct.
Okay.
So if I say that means we can't put the same color which are directly connected by age. Okay. So now we considered the coloring problem as a function C. Okay. Now, how can we express the problem mathematically? So it's like when UV is in E, that means when we have a edge from some vertex U to some vertex V, then C of U is not equals to C of V. That means color of U is not equals to color of V. Now it is it correlate?
Sure. But in that case, two colors are sufficient for any graph, right? Because you all alternately keep changing the color, then you end
No,
up in
not for any graph. Like if I have this age also, we can
linear.
have this
Okay.
type of age also.
Okay.
So for that we basically have a theorem. The theorem is called four color theorem. That means for any planar graph, we can like four color are maximum four color are sufficient to color a planar graph. Okay.
Okay.
So this is called four.
Planar graph means two-dimensional graph.
Yes, correct. So the statement of four color theorem is for okay. So the graph derived from geographical map means it will be a two-dimensional map, right? So for any graph which is two-dimensional, so four color suffices. Okay, that means we can color any planar graph if I have four colors, maximum four colors. Okay, so suppose we have this graph. Okay, so can you conclude how many color we have to use to color this graph? Exactly.
If we start with the vertex 1,
Yeah.
then if we start with some color 1, so let's say A.
Suppose we are coloring it with the red.
Yeah, I cannot color 2 with
Two
the same
with,
color.
right.
Yeah.
So we have to color 2 with some another, right? So
Yeah.
we can maybe put blue.
Yeah, but we cannot put blue in 4 and 3.
Yes.
But we can put red in either of them.
Actually, both of them, right? Because
Yes.
both of them are not directly connected with them. And
Exactly.
we need the minimum. So we can put red in both 4 and 3. Now?
And 5
can be
remains to
blue.
be blue.
Correct. So 2 color is basically sufficient to color this graph, right? Okay. We maybe solve another more problem. We can have a bit complicated graph. Okay. Now,
So we can
you
start with
again-
1 as red.
yeah,
So if we
we
start
can,
with,
we
yeah.
can start with a single color.
So 2 and 3 should be different.
Yeah. So we will immediately put the color, some different color to 2 and 3, right?
Yeah.
Yeah.
Blue and probably
And
No,
4
it
can be
cannot
green
be.
again.
Oh,
Three cannot be blue, right, ma'am?
correct.
Yeah,
Three has
3
to be
can
different.
3 has to
Because
be
there
different.
is a direct edge between
Yeah.
2 and
Yeah,
3. So
2 and 3.
2, 3 we can put red.
Can be red.
Yeah.
Yeah, 4
Yeah,
can be
here
green or blue.
green or blue.
Anything like.
Yeah, yeah.
Yeah,
So we can use green here. Yeah.
Yeah.
Then 5 can be blue or red.
We can put red.
Then this can be blue or green. 6 can be
Correct.
blue.
So 1 we can put green.
7 also can be blue, right? So
Yeah. It can be blue, it can be green, anything.
green. Yeah,
So if I use green, then the number of color is also remaining the same. So there is no problem, right? We can use green, we can use blue, anything, right?
yeah, yeah.
So basically the number of colors is 3 here, right?
3.
And here it was 2. Okay, so is it now clear? How can we deal with coloring problems?
Yeah.
Yes.
Okay. Now we have a new concept called vertex cover. Okay, so what is a vertex cover?
Hello. But
Yeah.
why do we, why we, color the, what is the
What?
need of coloring? Why we do color?
Okay, so suppose you have a graph, geographical graph, okay, and you want to color the graph. I mean, suppose we have the graph of India, so you have to put the color in each state. You can take each state as a vertex, and you have to suppose color the graph of India in such a way so that no consecutive states are having same color, because you want to define it properly, right? This type of problem you can deal with this coloring problem. Okay.
Okay, just to demarcation purpose,
Yeah.
we need to color.
Yes, correct.
Okay.
Okay. So next we have vertex cover. So what is vertex cover? It is basically a collection of vertex such that all edges can be covered. That means we will collect the minimum number of vertex such that not the minimum number of vertex. So we can collect any number of vertex so that we can cover all the edges. That means the edge associated with that vertex we can cover. Okay. So it's collection. Yeah.
But technically, the edges will come only when the vertex are available. So that means, are you saying we can leave some of the vertices without connecting the
right.
edges?
So
Okay.
that means we have 0, and suppose we have a edge between V0 and V2. So we can take any one of them, right?
Okay.
So if I take any one of them, then it will be a cover also, right? So why do we need that? We will solve an example.
Okay.
To see why do we need that. Okay.
Sure.
So the definition of this is basically collection of vertices such that all the edges can be covered. Okay. So we have the trivial vertex cover. And what do you think? What should be the trivial vertex cover? The whole vertex set, right? If I collect all the vertices, then automatically it will contain all the edges, right? Right. So if I have 4 vertices and suppose 3 edges, so if I take all 4 vertices, it will definitely cover all 4 edges, right? So this is called the trivial vertex cover. Okay. Trivial vertex cover is nothing but our V. That means set of all vertices. Okay. So for example,
can you? Yeah, example will help them.
Yeah. That is what I'm going to say. Yeah. So if I have some V0, V2, V5. Suppose this is our graph. Okay. Now we have to collect the vertices such that all the edges can be covered. Okay. Now, if I take all the vertices, it will definitely cover all the edges, right?
Yes, ma'am.
So this is the trivial vertex cover. And trivial vertex cover, there will be a trivial vertex cover for any graph, right? For any graph, if I take the whole V, it will be a cover. Now we can get another sets, right? So from here, if I just take V0 and V2, it will be a vertex cover, right? So if I take
Yes.
V1, that means these edges we are taking, and V2 means all the 4 edges we are taking, right?
Yes.
So is there any other vertex cover?
In this
Just to
graph, no.
clarify here, if you are considering this as a vertex cover, so if you are considering the vertex cover between two vertices, say you say that V0 and V2, so that would be only one, right?
Only one means?
So there would be only one vertex cover, right?
No, there vertex cover, there are so many vertex cover. Like the trivial vertex cover is a cover for that graph. The first V0 and V2 is another vertex cover. Also, you can define other vertex cover too. Like if I take V1 and V2, it will be another vertex cover, right?
Yeah, no, I'm just choosing this as a subset, like just taking this subgroup, like sub-element V0, V2. So for that, the vertex cover would be one, right?
I'm not getting it. If you take V0, V2, then
so there is only one edge that connects them, right?
okay. So if you want to take only this portion of the graph,
Yeah.
okay, then you can take only one number, only V0 or in only V2.
Yeah. Okay.
Okay, so it will cover. That means you have to choose one vertex which is connected with the edge. So only one vertex is enough, right?
Okay.
So here we choose V0 because we want to cover this vertex too, right? This is not connected with V2, right? So instead of V0, we can also take V1. V1, V2 will be another vertex cover, right? Is it
Right.
clear?
Yes.
Okay. So like that, we can consider so many.
What is the vertex cover for V3? It is only one, right?
For V3.
V3.
No. See, vertex cover of this graph. Okay. Vertex cover not for a particular edge.
Okay.
Vertex cover a graph is collection of vertices such that we can cover all the edges.
All the edges. Okay.
Yes. So here, when we are taking V1, that means V1 is connected with this edge, right? That means we are taking this edge. So this edge is covered. Now we are taking V2 and we have 4 edges which is associated with V2. That means we can take this 4 edge. So now if I take only V1 and V2, we can cover all the 5 edges here, right?
Yeah, got it. Thank you.
Got it? Okay. Another one also we can take. Yeah, any one of you, any other vertex cover you can see? Our motto is we want to cover all the edges, right? So accordingly, we have to choose some vertices. Okay.
No, there is only two set. V0, V2, V1, V2.
Okay. So another also we can take, like if I omit V2, then like
If you
vertex cover, we don't like here when you are finding the vertex cover, it's not necessarily you have to find the minimal number of vertex, right? Here it is just you have to find the possible covers. So what is another possible cover?
V0, V2, V5, V0, V2, V4, something like that.
So once you are taking V2, we don't need to take any V5, V4, V3, right? It is not adding any new edge to this, right? So when you are taking a number,
but we can take extra also, or we have to give only the exact those which covers.
Exactly. So if you take V2, then there is no need to take V5, V4, V3, right?
But
Because
if we take, is it a mistake? Suppose we take V0, V2, V5. Is that a
Yeah.
mistake? Or we can take for
no,
next time?
so you can't take, like, it is not the proper vertex cover, right?
Oh.
So vertex cover means when you are taking, that means like when you are taking V2, it is already covering this edge, right? When you are taking V5, it is again covering the same edge, right? So we
Okay.
can't take that. Okay. So here, if I don't take, suppose if I don't take V2, then there is another possibility, right? If we can also consider V0, V3, V4 and V5. This will be another vertex cover, right?
Yes, understood.
Okay. Yeah. Is it clear for all of you?
Okay, ma'am. Then can we say that this vertex cover is in the graph would be the condition if every edge is incident on a vertex in that graph?
Mm-hmm.
Can we say it this way? Because if I let's say if you're pulling out this vertex cover for V0 V5.
V0, V5.
Yeah.
Okay.
So there would be only one cover possible, right?
Wait. V0, V5 means like you are considering this graph.
Yes.
Then what are you doing then after that?
Yeah, I'm asking if there exists a vertex cover for V0 V5.
Okay, so V0, V5, so you are taking this portion of the graph then.
Yes,
This is our graph now, right?
exactly.
Okay, so we have again several possibilities, right? So if this is our graph, our aim is what? We want to cover all the edges. So we have only two edges, right? If I take only V2, it will cover the two edges, right?
Okay, yes.
Correct. Again, we can take V0, V5. It will again cover the V edges, right?
Yes, yeah. Okay.
Again, we can take V0, V2, V5. It will again cover the edge, right?
Right. Okay.
So
So our
this
aim
here,
would be to to cover all the edges that's there in the
yeah,
graph.
this is our aim, to cover all the edges. We can take any possibilities, but if I take this, suppose in this graph, if I take V0 and V5, suppose V0 and V5, is this a cover?
No, because
In this graph, no.
V3 and V4 will be missed.
Correct.
And V1 would miss too, I think.
Yeah. So
Yes.
if I take V0 and V5, we can only cover this edge, and this edge, right? What about this two? This two we can't cover with V0 and V5. So this is not a cover, right? Similarly, if I take, suppose, only V2 here, this will also not be a cover, right?
Yeah, sure.
No, because V1 will be missing.
Yes, correct. That means this edge we can't cover with only V2, right?
Sure.
Yeah.
Yes.
Okay. So again, we can maybe, suppose we have V2. What are the possible vertex covers?
Okay,
All
one
possible
would,
vertex cover we have to say.
V1, V2, V4.
yeah, V1, V2, V3, then V3,
V1,
V2, V4.
wait,
V2, V4.
V1,
V4,
V2,
V5.
V3,
V2, V2, V4, V5. V2, V4.
V2, V4, correct. V2, V4 is a cover. Is it a cover?
Yes.
How?
V2, V4. You're talking about V4,
No,
V2,
V5
V4, right?
is missing.
If I take only
V5.
V1, V2 and V3, is it a cover?
No,
No,
the
V5 is
V5 is
missing.
Yes. Right? This is a cover.
V1, V3, V5.
Okay. If I take V1,
V3,
V3,
V5.
V5. Okay. So if I take V1, it can cover this. V3 means it can cover this. V5 means it can cover this. But can I cover this edge with this covering?
No, you need to have V4 as well, or
Correct.
V2 as well.
V2 or V4.
Yeah.
At least
Okay,
one
okay.
of them, right? So this
Yep,
is
yep.
this is not a cover, right?
Not a cover.
Any other example like from here of cover?
I think we start with V1, V2, V4, V5.
V1, V2, V4 and V5. Yes, this is again a cover.
V2, V4,
Then-
V5.
Yeah, and V3, V2, V4, V5. That would be another cover.
So once we have a cover, okay, if I take any superset of the cover, it will be a cover, right? Agree?
Yes, yes.
Yeah. So any superset of a cover will be again a cover. Okay. So that means if I take any superset of V2, V4, it will be obviously a cover, right?
What is superset of V2, V4?
Superset means it will contain more elements than this. So it will include at least V2, V4, then it can contain more vertices. Okay. Is
Madam,
it now?
if it is V1, V2, and V4, is that not a cover?
V1, V2,
V2.
and V4. Yeah, this is a cover. Again, this is a superset of V2, V4, right? So you have
exactly.
to, yeah.
Exactly.
What do you have to check?
But V3 is not covered in this one, no?
No,
V1,
V3 is a vertex, right? What is our aim? Our aim is to cover all the edges.
Oh, V2. Yeah, got it. Sorry.
Got it?
Yeah, V2 is there.
Yeah. So when we are taking V1 means this edge, V2 means this two edge, and V4 means this edge. So all the edges are getting covered here, right? So our
And-
aim is to cover here. Yes.
Sorry. You continue, madam. I'll ask after that.
Okay. So the thing is, our aim is to cover all the edges. We will contain the vertices so that we can cover all the edges. Okay. Yes,
Okay.
you can ask your doubt.
Yes, madam, can we cover all the edges with minimum values? Will that help us to solve the problem, or we'll have to collect everything?
Yes. So minimum you have to like maximum we know it's a trivial set, right?
Yes.
That means if I collect all the vertices, then it will be the maximum, right? And
Correct.
if I can find the minimum cover, then it can solve some problem. We will solve a problem based on that. Okay.
Okay.
Before that, I need to just ensure whether this concept is clear or not. What is a vertex cover?
Yes, madam. Clear.
Clear?
Yes.
So the thing is, we have to collect the vertices so that we can cover all the edges. Okay. Clear? If you have any doubt, you can ask. Definition of vertex cover is clear, right?
Yes, madam. Clear.
Okay. Good. Now we can see the problem. So the problem is, suppose we can take all the straight lines, okay, and camera we have to put at the intersection of corridors. Is the problem clear? So a hotel that wants to install some security camera, and there are corridors, obvious, right? So we have to find the minimum number of camera the hotel need to put, right? So if I have intersection of corridors, suppose we have this type of corridor, and if I put a camera here, it will cover all the four corridors, right? Agree?
Correct.
Yeah.
Correct.
So it is a representation of this type of problem where we can find the answer of this type of thing, right? So if I calculate the vertex cover here, so vertex cover means we are basically covering all the edges, right? And if the hotel wants to install the cameras, that means they want to cover all the corridors, right? We can what we can do, we can represent the intersection of corridors as our vertex and the corridors as the edges, right? Now we can find the vertex cover, and the minimum vertex cover will be the number of cameras we need for this problem, right? So if I look at the same graph, suppose this is the graph of our hotel. Okay, suppose these are the corridors and this is the intersection points of the corridors. Then what is the minimum cover here?
It's
Two.
V2, V4.
Two.
Yes, V2, V4. That means if the hotel install two cameras, then it is enough to cover all the corridors, right? One is in this position and another is in this position, right? Okay.
Yes.
So you basically need vertex covering to solve this type of thing. So basically you have to represent the problem with respect to vertex and edges, and then you have to consider the small vertex cover. Okay. So whenever you will have this type of problem, represent it in terms of vertex and edges, and then find the smallest vertex cover. Okay.
Yes.
Yeah. So in this problem, we you have to read the problem and you have to understand which point you will assign with the edges and which point you will assign with the vertex. Okay. So in this, particularly in this problem, we will correspond corridors with edges and intersection of corridors with vertices. Okay, is it clear? The vertex
ma'am.
cover and the type of problem we can solve using the smallest vertex cover. Is it clear to all of you?
Yes.
Yes, ma'am.
Okay, then we have another thing, independent set. Okay, so what is independent set? So independent set is again a collection of vertices. If you have a graph, we'll collect the collection of vertices such that those two vertices we are collecting, they are not connected by a direct edge. Okay. So it is, the definition is basically it is subset of vertices such that no two are connected by an edge. Okay, so this is the definition. So it can be singleton, right? Example, let us see. Suppose we are taking this word edge, v1, then it is v2, v3, v4, v5, v6, v7, suppose this is our graph. So if I take any single vi, it will be an independent set, right? Agree? Any doubt? Agree?
Any single you're
How?
saying.
So if I follow the definition, what is it? The independent set is what? It is a subset of vertices. So if I take any one vertex, it will be a subset of vertices, right? And no two are connected by an edges. So if I take the single
connected by itself.
Yeah. So it's not connected by itself. So we can take the singleton, right? Now, what are the other independent set we can take?
Can you repeat, ma'am? What do you mean by not connected? No two are
It
connected by
is
an edge.
no two are connected by an edges.
For
No two
example,
are
if I
connected. Okay. For example, we can't, for this graph,
take
we
a
can't
V4,
take V1 and V2 or V4 together, right? Because V1 and V4 are connected by an edge, right?
Correct.
Yeah. So here we are taking the singleton set. So it is automatically will be disconnected, right? Obviously, V1 is not connected with V1, so we can take V1 here, right?
No two are connected by an edge.
Only one set if I take. So there is no other vertex which can be connected with it. So the singleton set will be automatically independent, right?
No, but the definition.
Okay, please. Yeah.
Yes. No, just start first.
Okay, so if we have this V1, V3, so it also forms an independent set, right? Or V2, V4.
Yes. No. V2, V4. Yes. Correct.
Yeah, but the trivial one would be the singleton one.
Yeah. So if I take only V1, only V2, like only any one of the point, that is why I write it as Vi for any I, then it will be automatically independent, right?
So because there will be no self loops possible.
Yes, right. Okay. So there is no edge between V1 and itself, right? V1 to V1. So if I take only the singleton set, it is an independent set. Automatically the singleton set will be independent, right?
But the definition is not as clear as, if you look at the definition, subset of vertices such that
no two are connected by
no two are connected by one edge. So
yes. So
subset
here
of
we don't have in another points. We have only one point here, right?
Where, ma'am?
Suppose you are taking only V1.
Okay.
So it is not contradicting the definition, right?
So subset of vertices, when I say subset of vertices, it can be one vertex or more than one vertex.
No,
right?
it
Because
can be one vertex. We can take singleton subsets also, right?
That is our choice, but I can always, for example, if I have 8.
This is one possibility. That is what I'm saying.
Right, then the definition seems to be more generic. It doesn't say singleton. It says subset of vertices such that no two are connected by an edge.
Yeah.
So in a vertices of 8 set, I can take you have chosen singleton, but I can choose V1, V2.
Anything. Yeah. You can take any subset.
But in that case, there is a connection between V1 and V2, right?
Yeah, we can take V1 and V2. So this will not be independent, right? But if I take V1 and V3, it will be an independent set, right?
Oh, okay.
So if I take only V1, it will be an independent set. Is it fine?
It can be singleton, or it has to be a vertex where it is not directly connected
by an edge.
Via edge. So as long as the two conditions are met, then it is called independent set.
Correct. Yes.
Okay, understood.
Now is it clear? So the singleton set are automatically independent, right? We don't need to check anything because obviously there is no self.
Yeah, understood.
And this will be another singleton. So
V1, V7, is it?
Yeah, V1, V7.
V1, V8 also, correct, madam?
V1, V8 also. So we can take any set, any subset of the vertex which are not connected via directives. Okay, so the two elements we can find so many examples. Try to construct example with 3 elements. 3 elements. Suppose we are starting with V1. Then we cannot take V2, V5 and V4, right? Agree?
Correct.
Okay,
Then,
V2, V5 and V4, yeah.
Yeah.
But V2 we can take, right?
We are taking V1.
Yeah. But
So
V2 we cannot take.
We cannot take.
take.
V5 also we cannot take. V4 also we cannot take.
Right.
But we can take V8, V7 or V6, any one of them, right? Right? We can pick any one of them. There are because they are not directly connected with V1, right?
But it is connected to V8 is connected to V7, no, madam?
Yeah, but we don't have V7 in our set. Right now we have only V1, right? So if I take V8, then we are taking V8, suppose, then we cannot take V7. So we have to then exclude V7, right?
Okay, so V6 can be added here.
Yeah, now V6 can be added here and V3 also can be added here, right?
Correct.
Right? Okay. So this is the independent set of 4 vertices, right? Any other example can you construct with 4 vertices, independent set?
To V4.
V4, okay. V4 once you are taking, that means
V5 and V7.
V5, V5, V7, then V2, right?
V2.
Yes, correct. So this is another set which is independent. Okay.
V6 can be taken, but you are only choosing only 3 triple. V6 can also be part of that, right?
No,
Subset.
we are taking V7, na?
Okay.
So V6 will not be there because V7 and V6 is directly, even also we are
Okay,
taking V2. V2 and V6 also directly connected by an edge, right?
Right. Okay.
So
Is it like this questions to be solved, madam, for the exams?
yeah, you can have some written problems and you have to convert them in this way so that you can use these things to solve this. Okay.
Okay, madam.
Yeah, I will again solve a example. I will let you see an example which can be solved using this. Okay. So yeah, is it now clear how if I have the graph, how can I take the independent set? Is it now clear?
Yes, madam.
Ma'am, if you see the last one example, where you're taken V1, then you're taken V8, V6,
Yes.
then you're taken V3. Oh, okay. I thought V2. Okay, fine, understood.
Okay.
Yeah.
Okay, we can maybe construct one more example. Maybe we can construct. Any one of you?
We can start with V3. So if you start with V3s and then V3, V1, V6 and
V3,
V8.
V1.
V6 and 8.
Oh, this is we already did.
Okay. So we can start with V4 that we already also have done. Okay, we can start with V5 as well.
Yeah, we can start with V5. Then
yeah, so in
if
that
I
case,
start
V6.
with V5, then we have to exclude V1, V8 and V6 first, right?
Yeah, exactly.
Yeah.
Then
so V3 will be there. V3, V2.
V3 we can take.
V3, V2.
That's it.
And V4.
No, we cannot take V3, V4 because V3 is connected to
Yes.
V4, and 7 and 2 are also connected to V3. So that's it.
Correct.
V5.
Right? So this is another independent set. Okay. Is it fine?
Yes.
Yeah. So V4 we can't take because V4 is directly connected with V3, right? So when we're taking V3, that means we have to, okay, V2 also we cannot take, right? V2 is also
Not
directly connected with V3.
To V3, yeah.
So only V5 and V3, right? Right?
Yeah.
Okay. So this is the concept of independent set. Now I'm writing a problem, sample problem, so that we can visualize the importance of this concept. Okay. So our example is okay. So this is the example. So we have a dance school here who want to organize a dance program. So we have maybe 3 to 4, like some number of group dances. Okay, and we have to organize we have to calculate the maximum possible group dance such that they can perform, and the condition is like one student can like one dancer can be a member of only one dance group. Okay, is the problem clear? Is the problem clear?
Yes, ma'am.
Okay.
Yeah.
So how can we represent the problem in terms of vertex and edges so that we can solve it with the independent set? So if we can represent this problem.
So how many students are performing in total?
What?
So we need to know the number of students who are performing in total, right?
Yeah. So this is a presentation. I mean, if you even like if you okay, let us see if I can represent the problem in such a way so that we don't need the number of students. Basically, what is the aim? We have to find the maximum number of dances, right? When we have to something like find something, try to focus on that point. Okay. So here the number of students in a dance group, it is not that important. Here the important thing is the maximum number of dances we can arrange for the program, right? So if I express the dances as our vertex, okay? So what do we want to use? The independent set, that means a number of maximum vertices, and here what is our aim? We have to find the maximum number of dances, right? So what we will do, we will assign the vertices as the dances, okay? And E will be, the edges will be oval. Okay, that means the vertices are the dance groups, okay? And the edges are like when we will have a edge between two vertex when the two dance will overlap. Is it okay? So the vertices are dances and there will be edge between two vertex when the two dance group is overlapping. That means the dancers are overlapping. Is it okay? So
Yes.
if I take the same graph.
If two dances are connected by an edge, that means both of them participate in one dance. Is that right?
No. So we are taking as dances. That means suppose we have dance group 1, dance group 2, like that, some 8 dance group. Okay. So there will be a edge from V1 to V2 if there are some common dancers in V1 and V2.
Okay.
Okay.
That the vertices are not individual dancers. They are dance groups.
Yeah, the vertices are dance groups.
Okay.
Okay. And E is the set of all dances overlap. That means the edge will be there in between two vertices whenever there will be some common dancers in these two dance groups. Okay. So if I take the same graph, so V5, V6, V7, V8, V1, V2, V3, V4. Suppose we are taking the same graph again. So here, all the vertices are representing dance group. Okay, that means suppose we have 8 dance groups. Okay, is it fine? Now there is a edge. If I take this edge is from V2 to V3. This edge is between V2 and V3, meaning there are some common dances in V2 and V3. Is it clear how we are representing the problem in terms of vertices and edges? Is it now clear?
Yes.
So basically, vertices we are representing as dance group, and E means there are some common dances between these two dance group. Now, what is our question? If I now check our question, the maximum number of dances possible, right? So the condition was like one student can dance in one, can join and only one group, right? At most one group. So if I perform V1, that means if I perform the dance V1, then at the same stage we can't perform V5, V4 and V2, right? Agree? If I perform V1, then we can't take V4, V5 and V2. Why? Because one student can perform in one dance only, at most one dance. So we are taking V1. That means there are some students which are in both V1, V2, in both V1, V4 and both V1, V5, right? Because they have a common age. That means there are some intersection between these sets, right? So because one student can only perform in one dance, that means we can't take V1 and V2 together, because then there will be some student who are performing. Yes.
If one student has to be in only one dance group, then
Yes.
there will not be any edges at all. No?
Yeah, that is what I'm saying. So if I take V1 and V2 together, that means there will be some student who are performing in V1 and V2 both, right? Right? Is it clear?
Yes.
So if we take, for example, if we take V1 and V2 together, then there will be some students or dancers who are both in V1 and V2, because we have a age connecting V1 and V2, right? So if I take V1 and V2, that means there are some students who are performing two dances, which is not possible according to our conditions, right? That means those are actually performing in two dances, which is not possible, right? Correct? That means what do we need to do? We have to take the maximum independent set here, right? That means to answer this problem, we have to compute the maximal independent set. Okay. So if I take the maximum independent set, so we already computed it, right? We can take V1, then we can take V8. So we cannot take V7 then. So we can take V6 and V. Suppose if I take this 4, this is a maximum. This is a maximal independent set, right?
Correct.
So that means this is a solution for this type of problem. Okay.
But one student should not be in more than one group. No, then how V1 and V8 can be taken?
So there is no direct age in V1 and V8, right? That means there is no intersection in V1 and V8. What is the expression of age? That means if there is any direct age, then only we can say there is a common intersection, right? There is overlap. That means there will be a direct age. But from V1 to V8, there is no direct age, right? That means there is no overlap.
Hello.
Yeah.
Madam, we'll have to assume these values, or how? What the inputs will be given?
No. Okay. So the number of dance group, you can take like the number of dance group will be given, and then according to this data you can follow this. Okay.
This is the maximum, means it should be 1, not the multiples. Maybe we can take V2, V5, V8, V4. We should not sum it up. Just
No,
only
no.
the maximum.
So we have to we have to compute the independent set also, right? A set which is the maximal independent set. So if I take V1 and V5 together, it will not be independent, right?
No, madam, I'm just asking. Actually, there are some probabilities, like, we can take V2,
Hmm.
V5,
Hmm.
V8,
Hmm.
and V4.
Yes, correct. So again, the cardinality is 4, right?
Yes, exactly.
Yeah. So what do we need? We need the maximum number of possible dance group, which is 4 again, right? For
Yes.
if you take any representation, the maximal cardinality will be 4.
Exactly. If it is 5, I'll have to take 5 if that is there.
Yeah. Yes, correct. So you can take different independent set, but the cardinality will remain same always, right?
Oh, okay.
So yeah. Okay. For example, we can take V1, then V8, V3, and V6, right? Which is maximal independent set. And the cardinality is equals to 4. That means what? We can take maximum 4. Okay, is it clear? How can we compute the independent set, the maximal independent set? And if I have this type of problem, how can we express it in terms of vertex and edges? And then we have to do this. Okay. So whenever you have to find some maximum, some minimum, so if you have to find some maximum number of something, that means you should think about the independent set, the maximum independence. If you have to find something minimum, then the last one, vertex cover, right? The minimum vertex cover, right? Which is not trivial. Here also, the maximum independence set is not trivial, right? So if you want to find something, the maximum, then you have to assign in this way, because here we wanted to find the maximum number of dance group. Also we can relate it with, if you compute the maximal independent set, that means the maximum number of vertices possible, right? So because the maximal and the vertices are connected there, so you have to you have to associate the dance group with vertex. That is how you have to associate the problem with the elements of graph theory, like vertices and edges. Is it clear?
Madam, the minimum how to calculate?
So if you have to calculate the minimum, then we need to check the vertex cover, right?
Vertex cover.
The smallest vertex cover, right?
Okay.
Yeah. Okay. Then we have another concept called matching.
I mean, if we have to compute this vertex cover here, that would be only, the cardinality would only be 2, right?
Yeah, cardinality will be 2. Yes.
Yeah, except for the trivial ones.
Yes. So if I consider the previous problem, so we have to take 2 cameras to cover all the corridors, right? If I consider the previous problem, so it was V2, V4, right? That means we need 2 covers. Okay. Okay, is it fine up to now?
So, ma'am, in the camera problem, minimum cameras required is a valid question, but maximum cameras required is an invalid question there.
Yes.
Right? Similarly, if I apply the same logic in this recent example, one which you explained about the dance.
Yeah. Yes.
So here, maximum possible dance programs is a valid question.
Yeah, but minimum is not.
Minimum is not valid in this question
Yeah,
because
automatically we can take any one dance group. It will be obviously the minimum.
obviously
right?
minimum. Okay.
Yeah.
Right.
And in the camera problem, we can take all the vertices. That means the trivial set here also the trivial set it will be automatically. So it is not a valid thing, right?
Yeah. Okay.
Okay. Any other doubt? Okay. Okay. So then next we have matching. Okay. So what a matching is? Now we up to now we are talking about vertices. Now we will move to edges. Okay. So matching is a subset of edges. Okay. So basically, we learned about independent set. If I just convert the vertices in independent set with edges, it is a matching, nothing but that, right? So matching is what? A subset of mutually disjoint edges. That means we can consider the edges which are not that means if I take the corridor problem, so we can take only those corridors which don't have any intersections. Are you getting my point? So that means we will consider only edges which are mutually disjoint. Okay. So if I take any example, suppose V0 okay. Suppose this is our graph. Okay. So if I take V0, V1, that means this edge we are taking. Now, if we are taking this, then we cannot take this edge and this edge, right? Because these two are not disjoint. These two have intersection, right? Also, we cannot take this one. This is also have an intersection with V0, V1, right? But we can take the other three. So if I take V2, V4 and V4, V2, that means this is what we are taking. So these two automatically we cannot take them, right? Because they have again intersections, right? So this is a matching. Okay, clear? Can you derive some other example from this graph of matching? This is one example.
Yeah, like we can pull out V1, V3, V1, V3. Okay. Okay.
V1, V3.
Yeah.
So if you pull out V1, yeah, that would
V3, V1 will automatically will be there.
there.
That means this is we are taking. So we have to exclude this,
Yeah,
right?
yeah. So V0, V2, V4 we cannot include.
Yeah. V0, V2 we can take, right?
Right. V0, V2 and V4, V5.
Yeah. V0, V2 we can take.
Okay.
That means V2, V0 will be there. That means we are taking this. So this cannot be taken. But we can take again this.
Just one thing, like V1, V3 we have taken. Yeah. So V1 also shares the common edge with V2, right?
Yes, but we have to we have to be focused on the edges. So V1 is sharing this edge with V2, right? So we can't take this edge, but we can take this one, right?
Oh, okay.
So we are taking the edges which are mutually disjoint. So this edge is mutually disjoint with this edge, right?
Then instead of V0, V2, we can also take along with V1, V3, V2, V4.
Yes. Instead of
V0, V2, we have selected V1, V3. Then we can select V2, V4.
Yeah, sure. They are also mutually disjoint, right?
Okay.
We can also take like V1, V3, V3, V1, then V2, V4, then V4, V2. That means we are taking this one, we are taking this one. So when we are taking this one, we have to cancel this 3 edges, right?
Yes.
We are cancelling the edges which have intersection with that edge. So this is what we can cancel. Now you are taking this means this one and this one we have to cancel, right? So if you are taking this two, that means this is the only possible set. This is the third example. Okay. Okay.
Yes.
Okay. So if I now okay.
Hello.
Yeah.
Is this the subset you are taking for any 2 points or how?
The subset is a subset of edges.
No, no. Actually, when you are doing it for V1, V0, V1, V1, V0, so you are taking these 2 points, V0, V1 with the edges.
Yeah.
So if this is a subset.
No, V not V1 means what? That means there is a edge from V0 to V1. That
Correct.
means this one we are considering. Okay. If it were a directed graph and only we had this, then we cannot take V1, V0, right? Because there, in this case, there is no edge in from V1 to V0, right? But here we have undirected graph, right? That means both the side we have. So we have V0 to V1 and V1 to V0, right? That means we can take the both.
Okay.
Yeah. Okay.
If it is
So, yeah. Yes.
I mean, all the concepts we discussed till now, I think almost all we discussed only about the directional, not directional.
Yes. Yes.
Both
Without direction.
Without direction.
Yeah.
So there is no similar concepts are not existing for directional. For example,
no, you can also do these things for direction. Like here, if you have like only one direction, suppose. Okay. Suppose this one we have, then we have to exclude V1, V0, right?
V1, V0. Okay.
So when we are taking,
write
it.
Understood.
So note. Vi, Vj is in the set E. That means there exists edge from Vi to Vj. That means this. Okay, this is the representation. Here we have undirected graph. That is why we can take both the directions. Okay.
If there is one directed graph V0 to V1.
Yes.
Okay. Then if we take V1, V3, we can take V1, V0. Is it okay?
Yeah, we can't take V1, V0. V1, V0 is not there in the set.
Yeah, but we cannot take V0, V1.
No.
So
we cannot take V0, V1.
Yeah, if we take V1, V3, we can take V0, V1.
We can't take this.
Sorry, we cannot take V0, V1, but we can take V1, V0.
Yeah. Okay. No, V1, V0 is not in the set.
Why?
The matching should be a subset of E, right?
Oh. There is no edge at all. Okay.
Yeah. So V1 is V1, V0 is not in the set E itself.
Okay.
So we can take it. Okay. If I have the directed graph also, first in the second example, we are taking this, means we have to exclude these 3. Agree?
Yes.
Yeah. Then we can take this, right? If I take this, then we have to exclude this. But again, we can take this.
Okay.
So V4, V5 and V5, V4. Is it okay now?
Yes.
Okay.
But
yeah,
if it is a directed graph, if we take V1, V3, we should not take V3, V1. We should take only once. No, here you are taking two.
If you have direction, like here, V1, V3 is the undirected edge, right?
Yeah. So you are taking
You
two.
have
If
both
it is
V1,
directed, we
V3
should
and
take only one.
yes, correct, correct. So here,
वो भी तो
here
नहीं तुम्हारे पास, वो भी
what?
तो नहीं है तुम्हारे पास, वो जो बोला है, वो बोला बेटा सुनो,
What? Are you
हम खाली
asking
चुप रहे,
something?
खाली तुम ही बोलो.
Okay. 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 Is it now clear? How can we choose the matching? Again, if I take only V1, suppose if I take only V1, V3 and V3, V1, it will be again a matching, right? Agree? It will be again a matching, right?
Yeah, exactly.
Yeah. So that means if I take only V1, V3, it will be a matching again, right? But it is as minimal, right? Again, for as like the independent set, in the case of matching also, what is not trivial is to find the maximal matching, right? A non-trivial thing is to find the maximal matching. Agree? That means maximal number of edges can be present in the set which are mutually disjoint. Agree? So what will be the maximal matching here?
Be 3, 4. No, 4, not 4. Wait. 6, I guess. Yeah, we can have
example 2, right?
Yeah.
So this is so when we have a graph, we want to compute the matching. It can contain any number of set, but there will be a upper bound of that, and that upper bound, the cardinality is called the set with that cardinality is called the maximal matching. Why we are using the maximal? Because there can be another set, another representation which have the same cardinality. That is why we are using the maximal. That means it is not the unique set. There can be another set, but the cardinality will be 6. That is what we are using maximal, not maximum. Okay? Clear? Is it clear to all of you?
Ma'am, can you repeat the last portion, ma'am? I couldn't understand.
Yeah, which one?
Maximal.
Okay, so it's like finding the maximal matching. It is not a trivial thing, right? The finding the minimal matching is trivial, right? You can take any edge, any one edge, single edge, V1, V3. It will be the matching, right?
V1, V3.
Only V1, V3. It is a matching, right? It is a subset of E and disjoint, mutually disjoint. It is again like similarly as the independent set, the trivial one, right?
Right.
So that finding the smallest matching is the trivial thing, right? It will automatically the singletons. But
taking any one edge will be the minimal matching. Any one.
Yeah, any one edge is the minimal matching. But the finding the maximal matching is which non-trivial here, right? So we have to work on it. So the maximal matching is like the maximal number of edges we can take such that they are mutually disjoint. Okay. And the cardinality is fixed, but the representation can vary. That means here we are taking this, there can be other, right?
But in this case, why you are choosing V0, V2 as a minimal matching? V0, V2, you're written as a minimal matching, right?
No. You can take anything, any single edge. You can take any single edge. It will be the
Okay, minimal match. Okay, maximal. Okay, maximal matching is what we have to find.
Maximal matching is example 2.
Right. Okay.
Right? So that why I just explained why we are using the word maximal, not maximum, because the cardinality is 6, but there can be other representations, right? So we can start with V0, V1, right? Then we can check others. Also, we can start with other, like there can be other representation with 6 cardinality, right? Are you getting the point? Okay. So let me draw the graph again. So we have V0, V2, V1, then V4, V3, V5. So if I take V1, V3, then V3, V1, V0, V2, V2, V0, V4, V5, V5, V4. So this is a maximal matching, right? Because there is no other set which has more cardinality than that, and there are like more cardinality than that matching. There are no other matching, right?
Yeah.
So this is maximal. And what is the cardinality? Is 6, right?
So this is with reference to taking V1, V3 as a starting point. But
yes.
if I chose, say for example, V4, V5 as my starting point, then it will be V2, V1, and
we can take this.
V2, V1 only.
We can take this.
Yeah.
We can take this.
That's all. That's all right, ma'am.
Yeah, but
only
we
4.
can. Yeah, only 4. But
only 4.
But we can consider other matching such that with 6 cardinality, right?
Yeah.
The independent set.
Correct.
That means the cardinality, the maximum cardinality is unique, but the set is not unique.
Okay. My only concern here, ma'am, is if you look at the first example and first sequence and the second sequence, which is first we picked up. No, ma'am. The same example. No, same example. Just hold on here. So if you look at the ma'am, just go up a little bit. No, not up. Sorry, not down.
Okay.
Further down. Yeah, just hold on here. So the first sequence we have taken V1, V3, and then we written down 6 combinations.
Yes.
In the second example, we took V4, V5, and we said in V4, V5 and V1, V2, though you are not written down, but it will be V1, V2. Now, given a graph, fortunately, we have chosen V1, V3 as starting point. We arrived at the maximum cardinality, which is 6. But assuming I wouldn't, without taking V1, V3, I would have chosen V4, V5. Then I would have landed up only with the cardinality of 4. Correct?
Oh, no. It is dependent upon the choice, right? Because
correct. So,
after V1, V5, V4, you are choosing V1, V2, right?
Correct. But that's a maximum.
You also have the option to choose V1, V3 after that. This is also not connected with V4, V5. No?
So my question is, in the exam, if the question is that we have to find the maximum cardinality, so we have to look around what is we have to trial and error we have to do to find out the maximum cardinality. Is that what my question?
Yes.
Okay.
Yes.
Understood.
Yes.
Okay, thanks.
Okay, so I just explained you why we are using the maximal. I guess you got the point, right?
Yeah, understood.
The cardinality is fixed.
Is there any formula to find what is the maximum cardinality?
Okay, so for this type of thing, these are some concept you have to understand. There is no formula, but after that, we will find some formula so that we can solve this problem using these formulas. Okay?
Okay.
Yeah. Okay. These are the basic developments. Okay. After that, we have some other formulas also. Okay. So
But
this
this
is
smaller, ma'am, for the smaller graph, we can arrive at the cardinality. But if, for example, if you have a large graph,
then you have to use the methods.
so
You
that I
will
think
learn about the method.
there we may end up into using a formula. But in the small case, it's easy to find out the maximum cardinality. For example, 6 or maximum 8 we can do. But if the same graph goes like beyond 20, 30, it is
Then it will be difficult.
If we keep on getting different sets, how do we know which is the maximum?
Can you repeat again your doubt?
If we keep on getting combinations of different sets for matching sets, how do we know which is the maximum one? Because
So,
first time we'll get 3, next time
you can
we'll get
try
5.
you can try different. Then after some point you will automatically get there is no
How
possibility.
do we know we have exhausted all the options?
No, so if you have a smaller graph, it will be automatically like under consideration, because for this graph we considered this the second example, right, with the cardinality 6, right? Now if I come like try on choosing this edges, then we can't be ended with something more than 6 here, right? If you have some smaller graph, then you can try it, right? But if you have the larger one, then there are some methods to solve this. You can use them to solve this. Okay. Yeah. Anything else? Okay, so now we have perfect matching, the new definition, perfect. So what is a perfect matching? A perfect matching is, first it is maximal, then it should cover all the vertices. Plus okay. So if I take this example, this is a perfect matching, right? It is maximal and it is covering all the vertices. V0, V1, V2, V4, V3, V5, all the vertices, right? So this is a perfect matching also. Is it okay? Any doubt?
Maximum cardinality is or maximal cardinality is a perfect matching, is what you're saying.
Yeah, look, the cardinality is not maximal. Cardinality is maximum. Because it is unique, right?
Yeah.
The set is not unique. That is why the set is maximal. Okay. So the perfect matching means it should be maximal matching. Okay. Maximal matching we know, right?
Yeah.
First of all, it should be maximal matching and it should cover all the vertices. That means all the vertices should be there in the set.
Okay.
So it is maximal matching plus it should cover all the vertices.
Vertices. Okay.
So in this example, all the vertices are there and this is a maximal, right?
But normally in maximal matching, you will end up in all the vertices covered. I think that's my guess. I don't know whether.
No.
So it's a possibility that you can still do a maximal matching
without covering all
the vertices. Okay.
There is some possibility.
So we have to find a combination which is both maximal matching plus all the vertices are at least one time it is covered in the subset.
And this is called the perfect matching.
Okay.
So the thing is, maximal matching exists for all graphs, but perfect matching may not exist. Okay. This is a remark. So if you have any graph, you can find the maximal matching. Maximal matching always exists there, but perfect matching may not exist. That means there may not always exist a maximal matching which are considering which are containing all the vertices. Okay. This is a remark. Is it fine up to now? Any doubt? No? Then this session will be a bit longer than the usual one. Okay, so you have to be a bit patient. Now we have a new thing, adjacency matrix of a graph. That means if I have a graph using the vertices and edges, we can form a matrix corresponding to the graph, and we may solve some problem easily with the help of the matrix. Okay, so how can we form the matrix for a graph? So suppose we have V, that means a set of vertices 0, 1 up to some n minus 1. That means set of n vertices, and suppose edges E. These are like I comma j, where 0 less equals to I, j less equals to n minus 1, and I is not equals to j. Because I is not equals to j, why? Any one of you can say the reason why I is not equals to j?
Yeah, that would mean self-looping, right?
Yeah,
so that's
correct.
not allowed.
Correct. So how can we form the matrix? It is basically A I j equals to 1 if I comma j is in E. Aij is what? It is the ijth entry of the matrix. Okay. That means the ith row and jth column, right?
But it says ij belongs to edge. So
yeah. That
edge
means
has
if there is a edge from I to j, then there will be a 1 in ijth entry.
Okay. So it's basically ij is nothing but the vertices, right? Two vertices ends of the
ij
edge.
has vertices, and the pair ij is the edge.
Okay.
So if I take, suppose.
What about the reverse, ma'am? When you have a reverse also, it will be 1 because ij is one direction, right? Or does it mean that it's both directions?
No. Ij means there is a edge from I to j.
I to j, but if, for example, it's not a direction, it's both directional means, then what is the matrix value?
Then edge ij is 1, but in that case, aji will be 0. All
Ji
other
will
entries will be 0.
Okay.
Okay. So suppose we have this graph. This is suppose our graph. Okay. And we want to find the adjacency matrix. So what is our vertex first? 1, 2, 3, 4, 5. Right? And what is the edge?
1, 2.
Suppose this is a directed graph, suppose, for example. Then 1, 2.
Yes. So 1, 2,
1, 2,
3,
2, 1.
2, 1.
1, 2, 2, 1. 2, 4.
2, 4.
3, 4. 3, 2, sorry.
3, 2.
4, 4, 5 and 5, 4.
4, 5, 5, 4. Then 3, 4 also we have, right?
Sorry, 3, 4. Yeah.
4,
3, 4 and 4, 3. Correct.
This is the edge, right? Now, what will be the matrix?
It will be a 5 cross 5 matrix.
So we have 1, 2, 3, 4, 5 here, and 1. Wait. One, 2, 3, 4, 5 here, right?
These are I and J, right? No?
Yeah, these are our I and J. So first of all, what about the diagonal entries? Let us start our thing with
That would be 0, right? That
all
would be
the
0 anyway.
diagonals will be 0, right?
0. Yes, because self-looping are not allowed.
Yeah. Now we have age from 1 to 2, right? Right? 1, 2 we have.
Yes.
That means A 1, 2 will be 1, right? According to the definition.
Yeah.
Aij is 1 if ij belongs to E, right? So A12 is means what? First row, second column, right? That means this entry, right? This entry will be 1. Okay,
sorry, it's 1, 2, man.
This entry.
Yeah.
This entry will be 1. Okay. Again, 2, 1 is there. That means this entry will be also 1, right? This one.
Correct.
Next, what about 1, 3?
No, 1, 3 is not there.
Correct. 1, 4.
1, 4 also is not there.
1, 5.
No, it's not there. 0.
Yeah. Then 2, 3.
2, 3. 2, 3 is not there. 3, 2 is there.
2, 3 is not there, but 3, 2 is there.
Yeah.
That means this.
Correct.
Right? So 2, 4.
2, 4 is there, but 4, 2 is not there.
So 4, 2 is 0, right?
Yeah.
2, 5.
2, 5 also not there.
0.
5, 2 also not there.
Yeah. 3, 1.
3, 1 not there.
3,
1,
4.
3. 1, 3 also not there.
Yeah. 3, 4.
3, 4 is there. 3, 4 is there. 4, 3 also is there.
4, 3 is also there.
Is
right?
also there. Yeah.
And then 3, 5.
3, 5 is not there.
4, 1.
4, 1. No, 4, 1 is not there.
5,
0.
1.
5, 1 is not there.
5, 2 is also 0.
Yeah.
5, 3 is also 0, but 5, 4 is there, right?
5, 4 is there. Yeah, 5, 4 is
And
there.
4, 5 is also there, right?
Yeah.
Okay. So this is the corresponding adjacency matrix of this graph. Is it clear? How can we form the adjacency matrix?
But why are we saying adjacency matrix? Because actually we have written exactly whatever edges we are able to see in the graph. For those edges we are given number 0 or 1.
Yeah.
But why we are saying adjacency matrix? Because I mean, I'm just literally going with the English language as adjacency is something which is adjacent to a certain thing. So if I apply that rule, there is nothing like we have done something which is adjacent here.
Yeah, that's true. So I also don't know the reason behind it.
Okay. I was curious actually why we are saying it's adjacent.
I think the reason is really being adjacent. You are counting the adjacent neighbors actually.
Okay,
so for instance, see here, if you go from 1 to 4, such elements are not counted. So you can go for if it's a directional graph, say we have an arrow pointing from 1 to 2 and 2 to 4, you can still go from 1 to 4, right? But there is no direct way. So, but here there is no in the adjacency matrix. This 1, 4 wouldn't have been 1 because there is no direct way to go from 1 to 4.
Yes. Okay.
Okay, ma'am. Right.
Yeah. So then we have a remark. If the graph is undirected, then the adjacency matrix will be symmetric. Can any one of you just give me the reason why is it so?
Because here
it's always reflexive.
Yes, correct.
Yeah, exactly.
It's a reflexive.
It's a reflexive.
The diagonal will be 0. So if undirected means if 1, 2 is 1, then 2, 1 will be a 1.
Yeah,
it should be symmetric, no? It should be symmetric.
Yeah, it
not
is
reflexive. Yeah, reflexive would be always 0.
No, okay. That means it will reflect with respect to the diagonal. I guess that is what you wanted to say, right?
Yeah.
Yeah. If the graph okay, so that means if I have undirected graph, then can we say anything about the cardinality of E?
Okay, so that would be twice the number, right? So you have 1,
No,
2,
no.
2, 1 occurring pairs.
It will be maximum, no?
The maximum possible cardinality.
Correct.
So whenever we have a H, that means we will have a 1 in this place, right? So that means the maximal possible cardinality cannot be the cannot basically the maximal. Okay, so if I have the undirected graph, that means the H, this is the maximal number is the maximal entry of the matrix, right? The maximal entry of the matrix, right?
Yes.
Yeah. So if I have these are some remarks, you just note it. So if I have an undirected graph,
Undirected means both directions, right? But
yeah, yes, then the cardinality of E is base equals to n into n minus 1 by 2, because we will have a symmetric matrix in that case, right? And we know the cardinality of a number of entries of a symmetric matrix, right? The order basically, right? Okay. It's
so
these are just some, yeah.
undirected is always a symmetric matrix.
Yes. Always the adjacency matrix will be symmetric.
Symmetric. Okay.
Yeah. So these are something you can note it down. Okay. So
just one question.
Yeah.
In this undirected graph, so we know that since it's a symmetric matrix, so the cardinality of the space of n cross n such symmetric matrices is generally n to n plus 1 by 2, right?
Yes, but we have to exclude the diagonal, right?
Okay.
We have to, because the diagonal will be always 0.
Okay. Yeah.
So if you exclude the diagonal, then if you calculate it, then you will get n into n minus 1 by 2.
Okay.
So basically, it will be the cardinality of the symmetric matrix minus n. So diagonal we will not.
Yeah, I got it. Yeah. So there will be n zeros will not count. Yeah.
What is n? So number of vertices or edges?
The number of edges.
Edges. Okay.
Yeah. Okay. So if I have the adjacency matrix, we can look after the reachability problem. Reachability problem is can we go from some vertex to another vertex, right? So if you have the question, can we go from 1 to 5? You can check the adjacency matrix to solve this, right? So if you want to go 1 to 5, so if we will check the row of 1, okay? So in the row of 1, we only have one non-zero entry, which is 2. That means we only have 1 to 2 another path, one edge, right? Similarly, we will check the row of 2. So first we have 2, 1 is 1, but this is not of our use, right? So we will check 1, 2 we will consider. Then 2, 1, we have reached to 2 now. Okay. Now we will see where can I go from 2. So if then we have to check the row of 2, right? So row of 2 means we have to check what are the non-zero entries in row of 2, which are 1 and 4, right? So we started with 1. So obviously we will not go back to 1. So we will choose 4, right? Then 4. Then we will again consider the row of 4. So 4 to we have 3 and 5. We wanted to reach from 1 to 5, right? This was our aim, right? Aim. So 4 to 5 we can go. This is a path from 1 to 5. So that is how we can, if you have the adjacency matrix, we can also look after the reachability problem. Is it fine?
Ma'am, going from 1 to 5, we started from row 1, right?
Yeah, yes.
So row 1, we looked at the whole row and we said in the number column 2, there is a 1.
Yeah.
So then we have converted that 1 into row 2.
Yeah. So that means we have 1 means there is a age from 1 to 2. Now
Correct.
we have reached from 1 to 2. Now we are at 2, right?
Yeah.
So now we will check where can I go from 2.
Okay. Then you have to look in the row 4, row
Yes.
2, sorry.
Yeah, row 2.
Row 2,
We have
column
2
4.
options.
Either from row 2 you can go to 1 and
Or
4.
Or 4, yeah. So
Yeah,
we will
1
not
and
go to 1, go back
1.
to 1, right?
Yeah, we have to go forward. So we'll go
We
to
have
4.
to go forward. So we will go 4.
Then we'll go to row 4 and
Row
we
4.
have to find, okay, we have 2 options, 3 and 5. So
5.
naturally we'll not go to 3.
Yeah.
We'll go to 5. So that's how you form the 1, 2, 4, 5
Yes,
path.
correct.
Okay.
Okay. So that is how, after seeing the adjacency matrix, we can solve the reachability problems. Okay.
Is this how the Google shortest path is calculated?
I don't know.
I'm just thinking aloud.
Google shortest path is not actually shortest all the time.
No, that I understand there are other constraints also, but in general, if there are no traffic constraints are there, I was just thinking maybe this is actually matching with what.
Yeah. This can be the thing. Like, this should be the base thing.
If you, for example, if I say my starting point is row 1 and I have to go go 5, then I have a choice of either 1, 2, 4, 5, or if I take a larger graph, I may have multiple paths. So what is the best path I can choose out of that?
Right. Yes.
Maybe the distances between 1 to 2, 2 to 3, 3 to 4, 4 to 5 can also vary, right? So depending on which route you're going.
Yes.
Understood.
So we can change the entries from 1 to some, we can represent it via the distance.
Interesting application. I never thought that this can be as. Okay, ma'am, one more question I have. If you look at this, no, one second, and just hold on there. So if you see this formula, undirected graph is E less than equal to n into n minus 1 by 2. You said n minus 1 because the diagonal zeros have to be accounted for.
Yes.
Now, if you look at the next formula, if directed graph is there, you are saying E is less than equal to n into n minus 1.
Yes.
Now, when you say directed graph, I can always have a hybrid graph also, no? Where I have few connections are undirected and few directions are directed.
Yes.
In that case, neither of the formula will be applicable in that case, right?
No. This is a case of directed graph. Even if you have few directed and few undirected, this is a case of directed graph.
No. What I'm saying is, if it's a completely directed, then it will be n into n minus 1. If it is completely undirected, then it will be n into n minus. But if there is a hybrid model, then neither of
directed.
No, it cannot be right, ma'am, because some are undirected, some are directed.
Yeah.
So how do we apply the formula there?
So some are directed means the graph is directed.
Oh, even if it's one directed is there,
then also
the whole graph will become undirected. Oh, sorry, directed. Sorry.
Yes.
Yeah. Okay. Can you put a remark, ma'am, so that when we go back and look at this,
yeah, sure.
It'll be easy for us to.
Yes.
Because it's a valid combination, right?
Yeah. Any directed age. Okay. So this
Okay,
is
ma'am.
the
Thank you. Thank you.
so now we have a degree of vertex. So for undirected graph, vertex is nothing but the number of this means number of the hatch basically symbolizes number of, okay, edges associated to the vertex. That is how many one is present in the row of the vertex. Okay, so this is the definition of degree of vertex for undirected graph. Okay, so for example, in this adjacency matrix, if I consider this graph, so what is the degree of 3 here?
1.
Degree of 3.
2.
Okay.
2, ma'am.
2, right?
Two ones have there, no? In the row of
Yeah.
3.
So the number of 1
Okay.
present in the row of that vertex.
Okay, I see.
Or, yeah. And in the above example, there are 2 ones present in the row of 3. That is, degree of the vertex 3 is 2, right? So for directed graph now, for directed graph, we basically have two different concept of degree, in degree and out degree, and it is obviously clear from the name itself. In degree means number of incoming vertex, and out degree means number of outgoing vertex, edges, right? For directed graph, we have in degree and out degree. So in degree is number of edges. That is number of 1 present in the column. Clear? Is it clear?
Okay. In degree.
In degree means number of incoming edges.
Okay.
So that means number of 1 present in the column. So
Okay.
if I suppose if I check the 3 and 3 to 2, okay, this is the undirected edge, right? Suppose if I want to find the in degree of 3.
3 to 2 is 1.
In
Sorry,
degree,
2.
so
3
no.
to 2.
Suppose we want to
0,
find
right?
we want to find the in degree of 2.
2. Okay.
It's
What
1.
is
In degree of
Swan.
2 is 2 to where, ma'am? 2 to which one?
Only
in
one,
degree,
right?
in
Once
degree
in the
of 2.
column 2.
Oh, okay.
In
So-
degree is 1, right?
In degree is 2.
In degree is
Oh.
also.
So if I check from the graph, we have 2 edges coming towards 2, right?
Okay. So, okay,
1
you are
to 2
also,
and 3 to 2.
yeah.
So if I check the column, we have 1 to 2 and 3 to 2, right? That means the number of a 1 in the column of 2. This is the
Okay.
Okay.
Oh, you have to take the second column and count the numbers.
Yes, correct.
Once in that. Okay.
Correct. So for example, in the above example, the in degree of 2 is 2, since there are 2 ones in the column of 2, right? Column of, okay. Then we have out degree. So out degree is what? Number of outgoing edges, right? Number of outgoing edges from that vertex. That means the number of ones present in the row of that vertex, right? That is the number of ones present in the row of the vertex. Okay. So what is the out degree of 2?
2, right, ma'am?
Correct. Example, the out degree of 2 is, okay. Is it clear now? Is it clear?
Yeah. But
Yeah.
But if the graph is not given and only the matrix is given, can we still apply the same rule
Yes.
incoming and outgoing?
Sure.
Because we don't know in the graph we can cross check whether it's a
it is directed or not.
But
So
whereas
if
you give a
the
pure
matrix is not symmetric, that means it is directed.
Okay.
Right.
So we have to
Also-
always look for a okay.
Okay. Yeah. You are saying something.
No, go ahead, man.
Yeah, that's the thing. So if the graph is undirected, that means the in degree and out degree will be same for all the
Same.
vertices.
So it will symmetric matrix.
Yeah. So if it
And
is
as you
symmetric, then the graph is undirected.
yeah,
Direct.
as you said, even if one is directional, then it will become asymmetric.
Yes.
Okay,
Correct.
understood.
So if I have the matrix, we can always find the degree of the graph. Okay.
Yeah.
Now we have 2 methods, and these are the most important thing from your week 10. It is basically a strategy for systematic exploration. That means if we want to explore the vertex, all the vertices of a graph, so there are some systematic strategies for that. That is, there are 2 basic properties, the ways to do that, and we will learn this thing. So first is, so it will also help us to solve the reachability problem. Okay. So that means we can find the smallest path to go from one vertex to another vertex using these things also. Okay. So we have 2 methods, strategies for systematic exploration. So we have two methods to do that. First is breadth first method. Okay. So we will say it as BFS. We will always write it as BFS. Okay. Breadth first strategy. And second, we have depth first, DFS. Okay. So today we will discuss breadth first only, and in the open session, I will tell Samiksha to discuss the depth first also. Okay. So today we will discuss the breadth first properly. So these are two methods we can use to solve this. Okay. So we will only discuss up to breakfast today because we need some more time to do this. So depth first, in the next session, Samiksha will discuss. Okay. So what is our aim? Our aim is to solve the reachability problem. Okay. That means we want to find the smallest path from a vertex to another vertex. And we can use these things. Okay. So this is basically BFS. So process. So first we can assume our set of all vertices as 0, 1 to n minus 1. Okay. So here we have to consider a chart. Okay. So chart of visited vertex. So we will consider a chart of visited vertex. Okay. So if a vertex is visited, if B is visited, we will write true, or if not visited, then we will write false. Okay. So we will initial stage.
All will be false, I think, right?
Yeah. All will be false. False for all the vertices. Okay. Then we will explore the vertices and we will write true. Okay. And we will continue up to the end stage. That means the stage when all the vertices are visited. That means true for all the things. Okay. And we will form a queue. Okay. So we will form a queue for explore vertices and continue the process we can set visited as true for all the vertex. Okay. This is the method. Now we will see an example, because it is difficult to get this from the method. So suppose we have the example. Suppose we have the graph. This is a bit complicated graph than the earlier one, right? So for this type of thing, we will basically use this process. Okay. Okay. So the first step is we have to initialize with a point, right? So we know that in the initial stage, all the visited vertex will be false. So we have to. So this is vertex and visited. Okay. So first we will list down all the vertices. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And all these are false initially, right? This is our first step. Okay. Now we will start with some point, and that point will be called as source. Suppose we will start with 7. Okay. This is our source here. Okay. So that means we will first visit 7. Okay. So when we visit 7, that means the visited will be converted to true, right?
Yeah.
So there will be 2, right? Now we have to form our queue. Okay. 2 explore queue. Now we have visited 7, so we will list 7. Okay, that means we have visited 7. Now we will explore 7. So we will explore 7 means we will visit all the vertex which are directly connected with 7. Okay, so in the note we can write explore 7 means we will see all the vertex which are directly connected with 7. Okay. So now we have visited 7. So if you explore 7, that means we have to visit all the vertex which are directly connected to 7. Then we have to explore all of them. So then
4, 5, 8.
4, 5, 8, right? So in
8,
the next step, our queue will be 4, 5, 8, right?
Yeah.
So next step, first we will write the visited thing. So the vertex and the visited. Okay. So first we will visit 4, 5, 6, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 7 we have visited. We now will visit 4, 5 and 8.
8, ma'am.
Yeah. And rest of the vertex will be false then, right? So what will be the queue then? 7 is done, right? Queue. 7 is done. So 7, we will exclude 7 and we will include 4, 5 and 8 now. That means we have to visit 4, 5 and 8. Okay. This is our next step. Now we will start with 4. We will initialize with the first point. So if I now I'm at 4. So which are the vertex we have to visit now?
3 and 0.
3 and 0, right? So in the next step, we will write true in 3 and 0, right? So true in 3 and 0, right? And in the next step, our Q will be, this is the process. So we have to explore 5, 8, and we have explored 4 and we found 3 and 0. So we will write 0 and 3 because we now have to explore 0 and 3. We have visited them, we have to explore them. And this is the process, we will write them later. Okay. So this is the process. Okay. Now 4 is done, right? Now we have to explore 5. 5 is already visited, we will explore 5. Now we are at 5. So which are the vertex we have to visit? 3 we have already visited. 3 we already have visited. 0 we already have visited. So we can visit 6. 8 is also visited, right?
Yeah.
Okay. Then 6 will be true, right? Right?
Be true, right?
So then 5 is also done. So in the next step, what will be the Q? 8, 0, 3, and from 5 we visited 6. That means 6 we will add. Okay. Fine.
Right.
Yeah. So now what is our, we can write it better. So 0 true, 1, 2 is false, 3 we have visited, 4 we have visited, 5 we have visited, 6 visited, 7 is the source, so 7 also visited, 8 also visited, but 9 we have to visit, right? 9 is false. Okay. But this is our Q. That means we will explore 8 now. So if I explore 8, but we have to visit 9, right? Right? That means we will visit 9. So this will be true. We will visit 9. And in our Q, we will add 9. So we have 0, 3, 6, and we will add 9. So this is our updated Q now. Okay. Similarly, we have to do till the end. That means until the Q is being empty. We have to repeat the process. Okay.
Yeah, so you have to also go through 0 and 1 and 2 as well.
Yes, correct. So we have to go up to the end until the Q is being empty. Okay. That means until we are visiting all the vertices. Okay. Now we have to explore 0. So if I explore 0, what are the visited vertices now? 1 and 2, right?
Yeah.
So then we will update it 1 and 2 as true, right? And we will also update our Q. So this is 3, 6, 9, 1, 2, right? Now here all the vertices are visited, but we have to explore 3, 6, 9, 1, and 2, right? So we will explore them. If I go to 3, is there any new here to explore?
No,
4
all of
done,
them are
5 done, 6
done.
right?
Yeah.
So here it is true means here it is also finished, but we will see how, right? So that means 3 will be gone. So we have 6, 9, 1, and 2, right? So we will explore 6. If I go to 6, then 3 and 5 are the option, but these are already visited, right? So in the next step, we will cancel 6 also. So the new Q will be 9, 1, 2. Similarly, 8, 9, we have 8. So 8 is also visited, right? That means we have 1, 2. Then we have to explore 1. That means we have 0 and 2, right? So 2 is already there and 0 is visited. That means 2. In the next step, 2. And 2 means we have to visit 1 and 0. So 1 and 0 is already visited, means in the next step, this is the empty queue, right? That means here the process ends. Okay. Any doubt in the process? Anyone? Any doubt in the process?
How are you selecting the value at first?
Which value?
7.
Okay, so you can take any point as a source.
Okay.
Any point. Then you have to repeat this process. Okay. So you started with one point, means you have to, in the next step, you have to visit the vertices which are directly connected with the edge, with the vertex. And then in the next step, you have to explore all the vertices one by one. Then you will visit new vertices, and in the next step again, you have to explore them. This is the process. Okay, you have to repeat the process. Clear?
Okay, madam. It is the continuous process.
Yeah, it is the continuous process. And if you can end it with all the vertices as visited, that means the graph is connected. Okay, so we can also comment about the connectedness of the graph. This is a remark.
So if one of the vertex is open-ended, that means it's only connected in one side, other side is not connected, then it is a open graph or an unconnected graph is what you're saying.
It is not connected. Okay. So the thing is, if all the true means you can visit all the vertex from at least from one of the vertex, right? So that means the graph is connected. Okay. If all the visited place are true in the end, that means the graph is connected. Okay. Now, using this process, we can also find the path from one point to another point. Okay. How? Using this process, we can find the path from one vertex to another vertex. Okay. How? So for this, we have to add a new info which is called parent. Okay. For this, we have to add new info parent. So what a parent is? The parent, for example, parent of 5 is 7. Parent of 8 is 7. That means we will go back to the immediate last step, and we will see the immediate last vertex, and this will be the parent of that one. Okay. So parent of 0 is 4. So first we started with 7, then we visited 4, 5 and 8, right? That is why parent of 4, 5 and 8 are 7. Okay. Then from 4, we visited 0 and 3. So parent of 0 and 3 is 4. Like that, we will check the parent. Okay. Is it clear? Parent of 3 is 4. So this is the example. Now, if I just continue with our same thing. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in the end, we can see all the visited place will be true, right? We have already seen it, right? Now we will list one more column here, the parent, the column of parent. So what is the parent of 0?
4.
It's 4.
Yeah.
Right?
Parent. What is the parent of 1? We can go to the
0.
queue.
0, I
No.
think.
We can go to the queue. So we explored 0 and we came to 1 and 2, right?
Yeah, it's 0.
Yeah, so it's 0. Similarly, for 2 also it's 0, right?
Exactly, 0.
For 3, it is 4. 4, it is 7. 7, we have noted it, right? So 7. 7 is our source, so we will leave it blank. 8 is 7. And what is 6? What is the parent of 6?
6.
5, right?
We got from 5.
Yeah. So we first we went 7 to 5, then 5 to 6, right? Here we can also see we had 5 here. We explored 5 and we are up to 6, right? So parent of 6 is 5 and parent of 9 is 8, right?
Parent of 9 is 8, yes.
Yeah. Now suppose we want to find the path from 7 to 2. So how can I find from here? We will start with 7 and we have to go to 2. How can we do that?
Following the parents.
Yeah, correct. So 7 means we have to check for which vertices the parent is 7. So we have 3 options, 8, 4 and 5, right? So we can choose this. If I want to choose the smallest path, which point should I take?
4.
Yes. 7 to 4 and 0.
So we can
7
go
to
to
4
4.
to.
Then we will
Yeah.
check the points for which 4 is the parent, right?
Yeah.
And also it should be connected with 2, right? So 4 is the parent of 3 and 0 both, but from 3 we can't go to 2 directly, but from 0 we can go to 2, right? Because the parent of 2 is 0. So from 4 to we will go to 0 because here 4 is present, and from 0 to we can go to 2 directly. Like that we can find the path using the BFS method. Clear?
This numbering is not in a proper sequence, right? It can be randomly chosen in the graph. Numbering 1, 2, 3, 4, 5, 6, whatever you've done.
Yes.
It is random. So when you are choosing, for example, from when you're going from 7 to 4 in this table, 7, you're looking at who are the parents for 7. So
no. For
sorry,
which
for which one 7 is a parent?
Yeah.
So we know that 4, 5, and 8 are 3 are having parent as 7.
Yeah.
Now in that 3 you have chosen 4. Is it because of the sequence of numbering? Because 4 is the least number?
No. It's not like that. So you have to see the shortest path because we want to go to 2, right? And 2 is connected with 0, right?
Okay.
So here
So
you can choose 8, but 8 is not connected with 0.
Okay.
Also 3 is not connected with 0, but 4 is connected with 0, right?
Okay.
So 4 is the easiest way we can choose
Right.
to go to 2.
Okay.
Okay.
Yeah.
Okay. Also, there is one thing, label. We can add one more column called label in our BFS to find the shortest path. Okay. So what is, we can add one node column level to find shortest path. Okay, so how? So the level initialization will be with -1 process. -1 for all j. Okay, that means for all vertices, the initial level will be -1 and source level of source will be 0. Okay, then in the next step, the visited vertex, we will in the next step we will add 1 with the next level. Okay, so if from source, if I visit the vertex j, if visit the vertex j from k, from some vertex k, that means level j will be level k plus 1. Okay, so we can see this in our example. Okay, so initially we have 0, 1, 2, 3, 4. Can you just wait for 2 minutes? I have to put charger on my iPad. Just wait for 2 minutes. Let me bring the charger and I will again start. Okay. Audible now?
Yes, ma'am. Audible.
Okay. Yeah. So what I was saying?
Talking about the levels.
Yeah. So we will initialize with -1, right? So the first chart will be -1 for all the vertices, right? Then in the next level, we started with 7. So 7 is our source. That means the level of the source is 0. So the level of 7 will be 0, right? Let us do it in the single thing. So in the next level, the level of level of 7 will be 0, right? And rest will be -1 again. Fine. And then we have the level of j. If we are visiting j from k, that means level of j will be level of k plus 1, right? So if we are visiting something from 7, that means we will replace the level of that point with 1. 0 plus 1 is 1, right? That means what will be the level in the next step?
So 4, 5, 8 would be set to 1.
Yeah, and so this will be -1, then 1, 1, -1, 0, 1, -1, right?
Yeah, right.
Then what will be the updated level?
Okay, so from 4 we visited 0 and 3. So,
yeah.
So 0 and 3 would be updated to 1. It would updated to 2 now. 2.
Correct. So 2. This is minus 1, right? Then 2. Then we have 1, 1, minus 1. 6 we have visited form. Who is the parent of 6? 5,
6
right?
we visited 5, yes.
So we know the level of 5. That means the level of 6 will be 2, right?
Yeah.
7 is 0. Level of 1, it is this. And the parent of 9 is 8, right? That means
parent of 9 is 8, yes.
8. That means 9 is visited from 8. So it will be 2 again. Right?
Right.
And what is the update in next step? 2. Then we visited 1 and 2 from 0, right? So what will be the level of this?
Okay, 1 and 2 from 0 would be 3.
3. Then again 3. Then 2, 1, 1, 2, 0, 1, 2. So that is how we started it. So what is it representing? The last one, what is it representing? It is basically the distance of the corresponding vertex from the source vertex. Okay, from the okay, that means what is our source vertex here? 0 means 7, right? So this is
Yes.
our source vertex. So the distance of 4, 5 and 8 is 1. That means it is connected by a single edge. That is why distance is 1. Similarly, 2 we can see like for 0, 3, 9 and 6. We have the level as 2. That means distance of these 3 vertices from 7 is 2. That means we need 2 edges to go from 7 to this 4 points. Okay. Similarly for 3, we can write it as a remark maybe. So that is, we need 2 edges to reach 3, 0, 3, 0, 3, 6 and 9 form from the source. That is 7 here, right? That means if you want to find the minimum distance from the source to any point, any vertex present in the graph, you can take that point as a source and do this thing. So you will find the distance from that source or that point to any other vertex of the present in the graph. Is it clear?
Yeah. So every time the source changes, the whole table has to be reworked.
Yes, correct. Whenever the source will changes, the label will be also changed, right? Okay. Is it fine? Is it clear to all of you?
Yes, ma'am.
Yes.
Okay. So it was all about the BFS method. I guess it is being late, so I don't want to uh, continue more. So if you have any other doubt, you just ask, and I ask Samiksha to continue from DFS. Okay, so if only we have DFS method and the definition of tree and the topological sorting. Okay, these 3 things we have to cover. So I will tell Samiksha to cover this in the next session. Okay. So to be covered DFS tree Okay, these three things we have to cover. Or if you have still energy left, then I can cover DFS. It is up to you. If you want to continue, then I will continue.
No, we can close.
What about others?
Yes, we can close, right?
Okay. Okay, so yeah. So it was up to BFS. Now, if you have any doubt, you just ask. Otherwise, we can close.
I have to solve the problems for this set of things.
Yeah. So after seeing this, you just try to solve the activity and all, and then let us know about your doubts in these things.
Okay.
Okay.
And this PDF will you upload, madam?
Yeah, I will upload in the drive. The link is present in the calendar. Na? I will upload there.
Okay.
Yeah. Okay.
This question, which is out of this, whatever you just explained, the syllabus content will be there up to 11, or week 12 also will be there?
No,
Content.
there is nothing week 12.
Week 12, only up to week 11. Okay.
Yeah, only up to.
So, okay, right.
Yeah, anything else?
It's better to wrap it.
Okay, so we can end.
Okay,
here.
ma'am. Thank
Yeah.
you.
Yeah.
Thank you, madam. Thank you so much.
Well,
Yeah, thank you, ma'am.
yeah. Good night, all of you. So we are closing this.